All right, welcome everybody. So today we're going to start our journey into electrochemistry by talking about galvanic cells. By the end of this lesson, you guys should understand how chemical reactions are used to generate electricity. You'll be able to illustrate that and even calculate the voltage of that flow of electricity that's being generated. So let's talk about it. What is a galvanic cell? So this is a device in which chemical energy is converted to electrical energy. And you might think, well, how do we do that? I mean, obviously, we knew when we were doing thermo that chemical energy could be used to generate heat or absorb heat, right? We had endothermic and exothermic reactions, but how's it going to generate electricity? Well, during a redox reaction, if you guys remember oxidation and reduction, electrons are lost by the oxidation and gained by the reduction half of the reaction. And so you have a flow of electrons. What we can do is we can separate the oxidation part from the reduction part and force that electron transfer to happen through a wire. So as the electrons are transferred from the species that's going through oxidation to the species that's undergoing reduction, that electron that's moving from one to the other is going to go through a wire. And what that does is that produces an electrical current that can be used to do work. There are lots of batteries that work like this. You have a lithium-ion battery in your phone. You have AA and AAA batteries that are typically made of nickel and cadmium. And so you have an oxidation reduction reaction happening there. And of course, those generate electricity, and you can put those batteries in all kinds of devices and use them to do all kinds of work. Now, they don't usually look like this, but if we were to build one in a lab, this is kind of what it would look like. And so when we draw galvanic cells, this is kind of how we're going to illustrate them. So again, what's happening is we're going to have oxidation happening in one place and reduction happening in another. And I know there's all kinds of stuff connecting the two. We'll get to that in a minute. So remember what oxidation is, right? Oxidation is losing electrons. So typically you have something that loses an electron and in the process forms a more positive ion. Okay? Then what happens is that electron gets picked up by something. So you have some sort of positive hooking up with that electron to form a less positive ion. So reduction is happening there. So what does that look like in our galvanic cell? Well, let's say that this metal strip here, because typically this is going to be a metal strip, is made of metal X. As oxidation occurs and those electrons are lost, those positive ions are going to dissociate into this solution that metal strip is sitting in. And so we're actually going to see this dissolving, and then those electrons that are being produced are going to travel across this wire. And they're going to go over here, and they're going to go down this metal strip, right? That's going to conduct that electron. There's going to be a positive ion that's already dissociated over here, and it's going to hook up with that electron. And then that can actually join up and hook up with this electrode here. And so what we can see sometimes is if the metal strip here is made of the metal that's dissociating, it's not always, but what we could see is we could see this metal strip starting to dissolve. And then over here, what we would see is it would look like this metal strip over here is growing because the ions from this solution are actually becoming solid metal particles that stick to this strip. So you could actually physically see sometimes this one dissolving and this one looking like it's growing, okay? So let's talk about the special names for these things. So the place where oxidation is occurring, that is known as the anode, okay? Place where reduction is occurring, cathode, gets a special name. We have a little acronym that helps us remember how this works. Fat cat. right? Can remember fat cat. So from the anode to cathode, right? Fat cat. We always have that electron flow from the anode to the cathode, and we have to show which way the electrons are going through this wire. So make sure you point the direction from the anode to the cathode. All right, so then what the heck is happening everywhere else? We'll see up here, this actually is a little box that could be attached to the wire measuring the voltage, measuring the current that's going across that. This right here is what we call a salt bridge. And it typically will be filled with something. So here I showed it in there, right? Here it'll be in here. And it is filled with a salt, an ionic compound that is soluble like KNO3. KNO3 is the most popular one because potassium is an alkali metal, dissociates, does not form a precipitate. Nitrate, soluble, dissociates, does not form a precipitate. Why do I need something that's soluble and does not form a precipitate? Well, let's talk about what's going on here. In the anode, what's happening is you keep dumping positive ions into this solution. So it's just positive, positive, positive. Well, that creates an imbalance of charge. You can't have a whole bunch of positives in the water. They need negatives there to balance them out. So what we're going to do is pull the negative part of this salt, the NO3 part, over here, and it's going to dissociate along with those positives and then balance out the charge in this beaker. Over here, what's happening is we're losing positives because they're becoming metal. And so we need to replace that positive charge because remember, this didn't dissolve by itself. There's no such thing as just Y positive in the beaker by itself. There's got to be some other kind of ion in there floating with it, you know, like chloride or something else, right? And so we're going to dump the positive part in here from that salt to replace the positives that are being lost. Because what happens is if you just have too many positives or too many negatives, if you have an imbalance of charge, reaction's going to stop. Those positives they're going to want to stay with the negatives in here. They're not going to want to go and hook up and become solid metal particles. So what we have to do is replace them in order to keep this reaction going. If we don't have the salt bridge there to replace the charge that's being lost on either side, the charge that's changing on either side, then the reaction stops. So that's the purpose there. Okay, so then the next page just kind of goes over all of it. So both the anode and the cathode are known as electrodes. Okay, so they might ask you which electrode is the anode or which one is the cathode. They're both electrodes. One is specifically the anode. That is where your oxidation is occurring. Right? Cathode is the area in which reduction occurs. Voltmeter, that's that little box up here, right? That's that guy up there with the V. There'd actually be a number on it measuring the electrical charge going on there. It is a tool that measures cell potential. That's what we call that charge, right? It's measuring the cell potential. Now this one gets a fun symbol. So curly E, ooh, that's fun. Cell. So E naught cell is the cell potential, of course, with that little knot there, measured under standard conditions, which we'll talk about in a minute. It could also be known as electromotive force, right? The force of electrons moving through the wire. So it could also be abbreviated EMF. Whatever, same difference. I mean, whether it's cell potential or electromotive force, whether it's E cell or EMF, it's typically going to be measured in volts. And just for future reference, in case we have to do some sort of conversion, a volt is 1 joule per coulomb. Oh, great. That's a new unit. There we go. So that name should look familiar. We discussed Coulomb when we talked about Coulomb's law, when we talked about protons and electrons in the atom and the attractive force between them and how it was dependent on the charge and dependent on the distance between particles. Well, Coulomb did a lot of work with electricity and got a whole unit named after himself. And so we'll talk more about that later. But a volt can also be represented as 1 joule per coulomb. So just be aware that that would be your your way of converting back and forth. Okay, so salt bridge. Salt bridge was the one that looked like a upside down U. Porous disc was the one that was like trapped between the two beakers. Anyway, it's a tube that's filled with an electrolyte, aka salt, aka ionic compound. Typically, again, you want one that's not going to form a precipitate, because if it does that and sinks to the bottom, then it's not replacing the charge. It's not doing its job of replacing the charge that's changing in the beaker. So you're going to pick an electrolyte, typically an alkali metal and nitrate, that dissolves to prevent the buildup of charge. Because again, if that charge builds up, cell stops. We don't want our battery to die, now do we? Okay, so this is good work here. Oh, there we go. Okay, so illustrate a galvanic cell that uses the following reaction in acidic solution. So this is a big idea, okay? All right, we've talked about redox. We've talked about redox in acidic solutions, right? So none of this is new. We're just applying it now to a galvanic cell. So remember, if I'm looking at a redox reaction and I'm trying to figure out what's the reduction, what's the oxidation, first thing I got to do, assign oxidation numbers. Now, obviously, these guys already have oxidation numbers assigned, right? My iron has a charge, my manganese has a charge. This permanganate over here, let's think about what we're going to do to assign individual oxidation numbers to the oxygen and the manganese. Well, oxygen has a rule. It's always -2 unless it's in peroxide. Now, -2 times 4 is -8, but I'm only allowed a -1 charge overall. So that means that this manganese here is going to be +7. So now we can think about what was actually oxidized and what was reduced, right? Oxidation is losing electrons, meaning it was becoming more positive. So just to recap, right? If it goes in this direction and becomes more positive, it's oxidized. If it goes in this direction and becomes more negative, it is reduced, right? On the number line, if the charges actually change in those directions, that's what's happening to it. So what was becoming more positive? That's going to be our iron. Iron was going from +2 over to +3. And that's a difference of 1 electron. So in the process, 1 electron is being lost. Now let's talk about this reduction, and I'm going to give myself some room over here. We have the permanganate ion becoming manganese +2. Now, obviously, that's not a balanced reaction, right? I mean, I know that it's going from +7 to +2, and the difference between 7 and 2 is 5. And so, you know, it's gaining 5 electrons over here to do that, but that's still not balanced because I have these 4 oxygens here. Remember, it's an acidic solution. We've talked about this. In acidic solution, you got water, you got H+. And so to balance out oxygen, let me add some waters to this side. I'm going to add 4 of them because I need 4 oxygens. And then since that gives me some random hydrogens that I got to balance out, there's my 8 hydrogens over there. So now this is all balanced up. Okay, so this is the reaction that's going to be happening at my cathode. This is the reaction that's going to be happening at my anode. So let's go ahead and draw it out. Okay, I'm going to do the porous disc one just because it takes up less room. And like this would be an opening. There'd be like, it's actually 2 beakers with a hole in the middle and then a tube that connects them so that liquid can flow in between, right? Because we need the salt there to dissociate into either solution. So it needs to be connected like this would be open, but it's just easier for me to draw a box. So whatever. Okay. And then of course, you know, I'd have an electrode here and then it'd be connected. And then I got my box and then some more wire. You like my little wire there? Cute. Okay. And then there it is. Yay, we're done. No, just kidding. We're not done. We actually have to like illustrate what's happening here. So let's call this one the anode, right? And that's going to be where my oxidation reaction occurs. And what's happening is, well, we have ions here. And so ions are going to exist in solution. So I've got some Fe2 pluses already floating around. So it's not exactly like the first one I showed you. This is not going to be made of iron because metallic iron with no charge is not in my reaction at all. So that strip right there, not going to be iron. Instead, we can pick a metal that doesn't react, so something really, really, really low on the activity series. And so typically the metals that are really super low down on the activity series are precious metals. And so we can pretend that this strip is made of platinum, right? Since it's not actually taking part in the reaction, we're going to pick something that's non-reactive. We could pick platinum. And all that platinum is going to do is allow the iron to come up here, dump off an electron, and go from iron 2 to then iron 3. So it's just providing a place for that electron to go. So that electron is then going to move across the wire there. So if you need a metal that is not part of the reaction to serve as your electrode, pick platinum. You're just drawing it. We don't actually have any platinum. I mean, that stuff's super expensive. Like I said, it's a precious metal, so, but it's free to draw it. So go ahead, feel free to draw it. All right, so those electrons go through the platinum electrode, right? The solution goes from iron 2 plus to iron 3 plus. Electron goes over here. What's it going to do? Well, again, we have MnO4 going up here and then becoming Mn2 plus. So it's actually picking up electrons off of this thing, right? And again, we're going to use platinum. Since I don't have a solid uncharged metal in my solution, then I'm going to pick a metal that doesn't react with anything, that's just going to serve as a place where those electrons can be absorbed by the permanganate ion. And so I pick platinum. Okay, great. So that's my anode. This is my cathode. Those are labeled clearly. Very nice. I am going to put my KNO3. And I'm going to show, let's see, this is becoming more positive, so I need to dump the negative part of the salt in here. So my NO3s are going to go over here. And then this is becoming less positive, because remember, this guy was positive 7, now he's only positive 2. So let me dump some more positives in here to balance out that charge. Okay, so there we go. All right, so I mean, this all looks really good. We've got the whole thing happening here, right? But my box is empty. I don't know what to put in here for the voltage. Right? We actually have to figure out what to put in that box. What is the voltage of this cell? So let's talk about how cell potential is calculated. What is that voltage going to be for this? So first off, cell potentials are already known, just like thermo values. They've been measured under standard conditions. Now, standard conditions are going to be 1 molar solutions of everything. It's going to be measured at 1 atmosphere. Also going to be at 25 degrees Celsius, just like our thermo standard conditions, right? And what we do is under standard conditions, reduction potentials. So how much energy is produced when the reduction reaction happens are going to be used to calculate E cell. So let's talk about this for a second. Here is what a standard reduction potential table might look like. Okay. You guys have a whole big standard reduction potential table in the back of your textbook. So you can look up standard reduction potentials in the back of your textbook. There's all kinds of reduction reactions there. You're going to find the one that matches your reduction equation, and that's going to be the value that you use. Okay? The way that it works is E cell, so the overall reduction potential for the cell, or I'm sorry, the overall cell potential is going to be measured by taking the reduction potential for your reduction reaction and subtracting the potential for oxidation. Well, wait a second, they're all given as reduction potentials. Okay, so check this out. Whichever species in a redox reaction, oh gosh, I wish it wouldn't do that. Okay, whichever species in a redox reaction has the more positive reduction potential is going to stay the reduction reaction. So you're going to compare the values for your reduction, reaction, and oxidation. And whichever one is more positive, that's going to stay reduction. The other one, the one that has the lower reduction potential, is going to be flipped around, and that's going to be the oxidation reaction. Okay, what? All right, so let me show you how this works. So back up here, we already knew which one was our oxidation reaction. I mean, obviously the iron was our oxidation reaction. So here's what I did. I went ahead and used the values in the back of the book and looked up reduction potentials. Now, I didn't find this equation in there, obviously, because they're all reduction potentials. I found the flipped version of this one. And when I found Fe3 plus iron becoming Fe2 plus, the reduction potential of this one, because they're all listed as reductions, the reduction potential of this one was 0.77 volts. When I looked up the reduction of the other one, it was 1.51. Now, obviously, that's more positive, right? So that's why this reaction stayed as I found it in the back of the book. And this reaction got flipped and turned into an oxidation reaction, right? Got flipped, turned upside down. So check this out. Remember Hess's law? When you flip a reaction, you flip the sign on it. It goes from positive to negative or vice versa. Well, that's exactly what happens here. I found it as a reduction potential with positive 77 as the value, but because I flip it and turn it into an oxidation reaction, I'm going to turn this guy into a negative, and then all I got to do is add those together. So negative 0.77 plus 1.51 gives me an overall E cell value of 0.74. Okay, so because they're all listed as reduction potentials, but I know this one gets flipped, I flip the sign on it, add them together, and that's my cell potential. And guess what, guys? That's what goes right here, 0.74. Ta-da! That would be the voltage on the cell. So there, we just illustrated a whole galvanic cell. And we calculated the cell potential, or electromotive force, if you will. All right, now listen, this could be done a different way, right? Now we had the overall reaction for that first cell that we drew, but now what they've done is they've just given us two reduction equations. Okay, so we have two reduction half reactions, and we need to figure out how this cell is going to be put together. Now they gave us a cell for these. So check it out. Using the rules we just talked about, I'm going to compare the reduction values because they're both reduction equations, right? They're both gaining electrons here. But if I compare them, I have positive 0.80, positive 0.77. Which one's the greater, more positive number? Well, it's this one. So this one's going to stay my reduction equation. And the one that had the less positive value, that one's going to get flipped around. Okay? And so this is going to end up flipping around. We're going to end up turning that backwards. It's going to be Fe2 plus becoming Fe3 plus and an electron. And then we're flipping the sign on this bad boy right here and then add them up, aka taking my reduction and subtracting my oxidation. Get it? And so this right here is going to give me an E cell value of 0.03. So not a huge voltage on this one. That's what it would be. Okay, now we need to include, so I got E cell, that's done, right? We need to include the balanced reaction. Okay, so balanced reaction, I already know that I am going to keep my silver like this, and I am flipping this bad boy right here. Okay, and remember the important part about balancing redox reactions. You have to follow the law of conservation of matter. Electrons matter, And I can't have 5 of them being lost in the oxidation reaction and only 2 picked up in the reduction equation. The number of electrons that are being gained and lost has to be equal. Remember, if they're not equal, then you multiply the whole half reaction. Now in this case, I have 1 electron being lost, 1 electron being gained, and when I add them up to get my overall reaction, they're going to cancel out because I have 1 on the reactant side, 1 on the product side. And so literally this one already was balanced. It's going to be Ag, the ion, and the iron 2 ion, forming solid silver and iron 3. Now I want to point something out. I do want to point this out. Let's go back to this first example we did, right? If I look back at this one, it actually wasn't balanced. You know what? I'm going to change colors on here just so you can see what I'm talking about. If I look at it, I had 1 electron being oxidized, 5 electrons over here being reduced. And so what we really needed to do was multiply this reaction by 5. Now they didn't ask us to do that. They didn't ask us for the balanced overall reaction at all. But if we had to have a balanced overall reaction, we would multiply this one by 5. Notice that I did not do that when I calculated the cell potential. I didn't multiply the reduction value of this equation by 5. Reduction values are not given per mole. We're not going to worry about multiplying them or whatever. I know I compared it to Hess's law and said when you flip it, you flip the sign on it. Well, in Hess's law, when we were doing thermo, if you multiplied it, you had to multiply the enthalpy or entropy value or whatever as well. We don't do that when we're calculating cell potential. So do not multiply it times whatever if you're getting a balanced overall reaction, right? Just add them up once you've identified which is oxidation and which is reduction. And if I was going to balance this overall, it didn't ask me to, but if I was, I can see here that I'd have to multiply iron times 5. So I'd end up with coefficients of 5 in my balanced overall reaction for my irons. And then the electrons would cancel out, so those would go away. But I'd still have my 8 hydrogens on this side and my 4 waters on this side. And so that would be my balanced overall reaction. But again, one more time, for the people in the back. Even though I multiplied this oxidation half reaction times 5, did not affect at all the way that I calculated my cell potential. So just keep that in mind. Okay, it's not exactly like Hess's law. All right, anyway, bada bing, bada boom, we got the overall reaction. So you know what, check, I can check that one off. Now I need to describe it. Okay, so a couple ways to describe it. I mean, I'm not gonna sit here and describe it in words. We don't use words in here. Words are overrated, okay? We are going to draw another picture, okay? Now you don't always have to put the anode on the left and the cathode on the right. We've got silver up here first, so check it out. I'm gonna put silver over here. What is silver doing? Silver is going from silver plus and becoming solid silver metal, no charge. So you know what? I'm gonna make my electrode right here solid silver. Ooh, fancy. We obviously don't have any of those sitting around, but that's what would be happening. The silver ions would be coming out of the solution, hooking up with an electron and forming neutral silver metal that's going to precipitate right here on this electrode. Now it needs electrons to do that, right? Where are the electrons coming from? They're coming from iron. Now, there's no uncharged metallic iron over here. Instead, what we have is Fe2 plus floating around, right, dissociated. Because ions they're not solids, okay? They're dissociated ions in liquid, okay? And so that was already dissociated in a liquid, and it's going to have to go up to this electrode, dump off an electron, and become Fe positive 3, which means that this is probably not iron right here. Again, we're going to pick platinum, which is an inert metal that's not going to react with anything. It's just going to serve as a conductor for that electron. So this guy is, doing the oxidation, which means that it's producing the electrons. Let me do my cute little wire, okay? My wires and clouds both have the same shape. It's just I'm an artist. Okay, so anyway, the electrons are being dumped off by iron. So this time my electrons are actually going, that turned out to be an error. They're going in this direction. right? My electrons are going from my anode, which is over here, to my cathode over here, right? Because this is where oxidation is occurring and this is where reduction is occurring. Doesn't always have to happen left to right, okay? Ooh, we're missing something. Well, we're missing the 0.03 here. There, now I know what the voltage is going to be on that one. We're also missing the porous disc with salt. Again, I'm going with KNO3. Now this is becoming less positive. So let me add some positives in here. This is becoming more positive. So let me balance it out with some negatives. Let's throw the NO3 in here. Okay. And then there it is. There is my galvanic cell. Now there's a way that we can describe it without drawing the whole picture. We can describe it using line notations. So again, line notation is going to go from anode to cathode and describe it very simply. What's happening here? Ag plus becoming Ag, Fe2 plus becoming Fe3 plus. Now this is the anode over here, so this is how I'm going to write it. Fe2 plus is becoming line Fe3 plus. So this is how it started at the anode, and this is the product that we ended up with over here. Now check this out, line, line. Now we're going to describe the change taking place at the cathode. We are starting with Ag plus. That was our reactant. Line. We ended up with solid silver product. So this is called line notation. You always describe the anode first, what you started with, line, what you ended with. Line, line, then you describe the cathode. What you started with, line, and then what you ended with. You can see why it's called line notation. So that's a different way that you could describe it without drawing the whole picture. But if you need to draw the whole picture, now you know all the parts and you could draw them yourselves. And I hope this really fully explains to you guys how a galvanic cell is used to generate electrical current, how that electrical current can be calculated, the purpose of the salt bridge, and all that jazz.